Hello everyone, thank you so much for joining us today. Welcome to the last webinar of the year. This month we're going to be talking about smart tunnel monitoring, reducing construction risk and supporting effective long-term asset management. So before we begin the webinar, I just want to run through a few housekeeping notes as always. So we will be having a short Q&A session at the end of the webinar, but please do feel free to pop your questions in the question box as the webinar goes along, and we will answer them at the end. And just to let you know, everyone that's registered for the webinar will also be receiving a recording. So I'd like to now introduce you to our speaker today, Marcus Rennan. Marcus has a background as a surveying engineer. He spent a decade in Iceland overseeing comprehensive monitoring projects, including large-scale tectonic plate movements and construction projects. Returning to Germany, Marcus joined VMT as a tunnel specialist, where he worked on numerous international assignments. Since 2020, Marcus has been a valuable member of Sensive. In his role, he has contributed to many successful wireless monitoring projects, helping clients enhance the safety and longevity of their infrastructure. Okay, over to you, Marcus.
Yeah. Thank you for this warm introduction. I'll, just like the subject says, dive underground immediately with this tunnel monitoring presentation. It's very general, I would say. Well, if we have a tunnel or a tunnel is constructed, basically we have impact on the surface above and the zone around. Let me switch the laser pointer. The zone around it that affects, basically, we are digging a long hole that destabilizes the ground and, of course, affects the surroundings here. This can be modeled, for example, like here in a finite element model, and by certain formulas and experiences, we can estimate and predict the behavior. These models nowadays are used to create monitoring models. Here, basically, as in the modern way, as an observational approach, meaning that we have a certain model of impact of ground disturbance. This model is basically by continuous acquisition of sensor data checked. This data is used for verification of the model or modification of the model, and new parameters are defined so that we can basically continuously renew this the monitoring scheme. Basically, monitoring is done in order to mitigate risk, and risk is defined of an undesired event that is caused by the measure taken. And of course, there is an economic aspect of it. So basically, we have here this kind of scheme where we draw the probability of an unexpected event against the severity. And it's a very simple idea. So if we know that the probability is high and the impact is high, then of course we have to modify the design of the project. If we have a very low probability with a high impact, we might be able to engage an insurance company. Or if the impact is low and the probability is low, we might even accept the risk that we, for example, have to repair a facade or so. But basically, when we know that and we can actually control the severity, then we might consider monitoring. And with modern approaches, of course, this has to be cost efficient. So basically the threshold between accepting a risk and repair it afterwards and introducing monitoring, may be manual monitoring or automated monitoring, depends exactly on this threshold. And as we, with modern monitoring equipment, for example, what we present as Sensive equipment, we are basically lowering this threshold by costs. not only in terms of hardware and software, but particularly in installation simplicity and operation and maintenance. Because if you have an automated system and you very often have to go there and clean it or repair it, replace equipment, then well, in general, I assume that there are a lot of people here, of course, are from the tunneling business, so I will go pass through these kind of general topics of different phases in a, as I call it, tunnel's life. It's the advance of the tunnel, the construction of the tunnel, the operation of the tunnel. At some point, the observation of the structural health of the tunnel. And of course, we might enter into a phase of the tunnel suffering from aging and needs refurbishment, which of course can impact the stability or the structural integrity of the tunnel itself. Then, of course, we have to, if we do monitoring, then we have to deal with certain specialties of the tunnel environment that affect, of course, the monitoring itself. Then we, of course, in a tunnel, we have to deal with the confined space. We cannot access the tunnel from the outside, like we can, for example, access buildings, looking at the buildings from the outside. We have to deal with the tunnel climate, which is in many cases very challenging, not only in terms of, like here, moisture or humidity in the tunnel with hot water temperatures, machines working, but also in terms of dust, or so that, for example, sight in a tunnel is very limited. We struggle with the outside reference. Any surveyor knows that, of course, we would try to access or place reference point around our area of interest, which, of course, we can only access from the tunnel entry or for a completed tunnel from both tunnel portals, but we cannot access usually the tunnel in the middle. So we have to deal with references. And of course, then if we install equipment, then it should not interfere with the operation of the tunnel, which means that we have to deal with the limited space in the tunnel. Yeah, and then in general, of course, maintenance access, that if the tunnel is under operation, in this case, of course, my picture here with the water, but in general, it could also be like a traffic tunnel where you have to deal with train traffic, car traffic, or so. That maintenance is not so easy, specifically in terms not of maintaining the tunnel, but maintaining a monitoring system or manual surveys for monitoring. Then, of course, we have different types of tunnel, specifically significant during construction. It's conventional tunnels by road headers or drill and blast, TBM-driven tunnels, either gripper with a natural integrity by the surrounding rock, or EPB, earth pressure balanced tunnels with a softer environment, usually then the tunnel stabilized by segment rings. We have pipe jacking tunnels, usually very small, small diameter tunnels, crossing, for example, infrastructure, driving underneath a channel, underneath a building, underneath a rail track, but usually also then pushed forward and with certain impact. And then sometimes very special tunnels like immersed tunnels, which comes in fixed prefabricated segments. Now, when dealing with monitoring, then of course we have to think of the different phases of monitoring, and this is something that's general for monitoring. We have to have a baseline monitoring, a vigilance zone. So we have to define what happens actually before any kind of impact, any kind of construction starts, and then we have a more or less phase where not so much is happening and we experience the natural behavior of our environment. And then when it comes to the active, for example, construction phase, then we have to observe the area and see what happens. And then after the tunnel is completed, the construction measure of tunnel construction or construction adjacent to a tunnel, we have to then have a closeout phase to figure out when basically any impact on the tunnel or the environmental infrastructure basically decreases. And then, of course, one part is, if desired, that we have life cycle monitoring for all of this. There are suggestion code of practice available that recommend certain measures. So basically, we have, for example, during a tunnel construction, these kind of phases with the advance here, in this case of a tunnel boring machine. We observe the vigilance zone, and then we install certain monitoring equipment, extensometers, inclinometers, total stations, and so on. And then we have a certain impact, and what we expect from a monitoring system, that it observes these impacts, shows us the behavior. Then when crossing certain threshold values or exceeding threshold values, then alarm messages are sent out automatically, so that nobody has to watch the system, but just trust that it permanently observes the system. And there are certain examples for, well, there's a whole catalog of basically tunnel related events. Here in this case, for example, very critical in Germany, the collapse of the town's archive with where two people died in Cologne in 2009, or relatively recently, where the how do you say, icing of the ground here in Rastatt near Karlsruhe in Germany failed, and you see that they led to deformation of the surface above, detected in that case early enough by this total station monitoring. Here are the prisms along the rail track, so that basically nobody was hurt. As much as it had impact on the infrastructure itself, it was from the point of monitoring, it was a success in early warning. So basically, we have the situation then, as said, we can calculate models of the behavior if we know something about the ground, and predict the zone of influence, and then place certain equipment within the zone of influence and extend it towards the outside of the zone of influence for reference purposes. That could happen, of course, by classic geodetic total station observations, like here. This is in Karlsruhe, where we observed the buildings. Underneath there was a tunnel boring machine running, and we observed the buildings in the vicinity, in the area of impact. But it's obvious that for these kind of observations, one requires the line of sight. And for example, this picture above is in Switzerland, where the prisms were covered in snow occasionally, and that, of course, either leads to a lot of maintenance, clearing the prisms, cleaning the prisms, or alternative approaches like, for example, tilt sensors mounted on the sleeper of the rail track. Observing, for example, also here, tilt nodes observing masts and all kind of infrastructure in the surrounding. Installation of this kind of equipment is rather quick. Here in the right picture, we have redundant observation, meaning that we at the same time have total station observations as well as tilt observations, and tilt observations by these kind of nodes. Here, in this case, it was an interesting situation, as the total station was stolen twice. So actually, the initially secondary tilt sensor system was promoted to the primary system for observations, and the total station observations were only carried out occasionally afterwards anymore. Installation, as I said, is very easy. The nodes are glued to the rail track, which of course applies similar to other construction measures, gluing or screwing them to a wall where they provide that relative movements, like here, for example, in a consecutive line of observations, providing cant, twist, versine measurements, or even on a acceptable accuracy level vertical displacement. Well, that refers also to infrastructure and buildings above. So also here, these observations could be carried out by total station observations with certain prisms or reflex marks. But like here, but if obstructions are there, like for example on this building here where the scaffolding was set up, then of course it gets more difficult, and the effort, particularly for manual monitoring, is already high, but for automated monitoring can exceed any acceptable level, and there it might be very helpful to not depend on optical line of sight, like here with the tilt node and here with the crack sensor, to monitor this kind of gap. For example, here on that is actually on this building here. Well, coming back to immediate tunnel impacts, this could also involve different kind of sensors. So departing from the geodetic observations, we come to the geotechnical part, where, for example, we have pipe drillings here, where borehole inclinometers are inserted. Observation can be carried out manual, but of course that involves personnel that regularly goes there, and particularly if the interval between the measurements gets very short, then of course manual surveys are not so efficient anymore. Here in this case, inclinometer measurements, providing the horizontal displacement along a borehole. But there we can also add automatic equipment. This equipment then being connected, this IPIs, in-place inclinometer, connected to this kind of node, the node collecting the data, submitting it to a gateway, and from the gateway automatically transmitting it to a web platform where everybody interested and authorized has access to the data. The same, of course, applies to extensometers, where you can have different types of extensometers with certain lengths of rods. You can have manual readouts with people going there, but this could also be collected by these kind of nodes where the data goes in and is submitted, as I mentioned before, to a certain threshold. Same applies, for example, to water level, groundwater level, ground pore pressure, so which can be measured manually by these kind of drum of cable plummet with a certain signal recognized when it touches the water level. But also this on the left is a picture from a recent installation above the Holstein tunnel in Germany, where a number of boreholes, water level boreholes, or groundwater wells were installed above the alignment of the tunnel, and now permanently the water level is observed by piezometric vibrating wire sensors. And with this node, the data is then transmitted to a central server, where the data can be then analyzed by whoever is interested and competent to do so. Well, if we look at the tunnel itself, there are outside forces affecting the tunnel, and usually the tunnel lining, the tunnel lining's job is to divert these forces. And as these forces, of course, have impact on the change on the tunnel itself, on the shape of the tunnel section, the tunnel section has to be observed. Here we have basically a lined, a segment lined tunnel, but also these kind of horseshoe shaped tunnels diverting the forces to the outside. And in this case, on the right side, the job was that this tunnel was renovated or refurbished. And in order to install electrification, the tunnel sole had to be lowered, and that had direct impact on, of course, the distribution of forces along the tunnel shape. So this was observed here in case convergences were measured, classically measured with this draw wire device. But one method is, for example, geodetic, observing prisms installed there. But what I try to illustrate here with this drawing is that, of course, the longer you aim into the tunnel climate, dust, steam, whatever it is, moisture, can affect the line of sight, and therefore it makes sense to overcome the limitations of limited vision. Here, or picture you have already seen with the hot water temperature and steam in the tunnel, that we rely then, for example, on shape arrays that can measure the deformation of the tunnel by tilt sensors inside the shape arrays, or here in this case, convergence measured. This is a Spanish tunnel by laser distance units here in this triangular shape. You see these devices here mounted, shooting to a target on the surface, downwards to a target here on the side, and horizontally through the target. And then you can, of course, monitor this data permanently. Can monitor this kind of deformation of the tunnel permanently in rather tight intervals, like half an hour, 50 minutes or so. So you're permanently aware of any deformation. In segment-lined tunnels, the segments themselves can be used as significant pieces as compared to the deformation of the tunnel, which happens in the joints. The segments themselves can be considered as rigid, and mounting tilt nodes to these individual segments, one can create installing tilt nodes here on the top, or even very small, in our case, nano nodes that are screwed with this specifically designed brackets into the screw holes here. And then we can design, assume a perfect initial shape, like here the circular shape, assume that we build between the joints out of these rigid segments a closed polygon, and as the shape deforms here on the right side, we can recalculate the deflection angles between the different segments, and by that calculate a new shape of the polygon with new coordinates, and between these coordinates calculate changes of distances with which represent then the convergences observed. And this whole thing can then, for example, directly be imported in the tunnel navigation system. So during advance, whoever drives the TBM has an idea of what's happening in the back of the tunnel by the outside forces. Well, talking about forces, of course, one concrete strain is always an issue. Here on the right side, strain gauges, vibrating wire strain gauges on a bridge, but also here, as in the steel reinforcement of the segments, can be installed right during implementation of the strain gauges can be implemented right during casting of these segments. So then we have some kind of an interface here where the data is then submitted to a gateway. And by that, the deformation of the individual segments can also be observed and then reflects basically the impact of the outside tunnel forces. The deformation itself, of course, can be can lead to displacements in the joints of this kind of tunnel, which can, of course, have significant amounts. The scope of this displacement can be significant, which of course then destabilizes the tunnel, and we can use automated crack sensors to measure these kind of displacements. This can be done in this one on the left would be one-dimensional, but this can by orientation, a different orientation of the crack sensors can also be done in 3 dimensions, which also, for example, is for immersed tunnels, that the 3-dimensional displacement of individual segments against each others can be monitored permanently. Yeah, and other manufacturers also provide devices like this one from Cisco, a so-called 6D device, measuring relative rotations and displacements of adjacent elements, whatever it is, or if it's a segment of a tunnel or construction site devices or so. A little bit more here, 2-channel node connected to 2-dimensional observations of this joint here of a tunnel. As we talk about relative displacement, of course, the dimension of vertical displacement is very important. If, for example, like here in a pipe jacking tunnel advance, then we want to know, basically what we do is when we drill a tunnel, then we, as I said, it's basically a long hole, and the density of the long hole is, of course, less than the outer area. And if this tunnel is drilled in water, then the tunnel itself will uplift. And this is a very dramatic picture of this. This is a water hydrant. And that was actually connected to the tunnel underneath, the water tunnel underneath. But due to the uplift of the tunnel, this hydrant was pushed 6 meters out of the ground. So it's obviously rather significant also to monitor the vertical displacement of a tunnel underneath. This is a part of the prior to Emisor Oriente in Mexico City, what the situation of water tunnels was there. And for this kind of measurements, one could use, this is a picture I stole from VMT, you can use hydrostatic leveling systems, basically using the water static height difference, the pressure, to measure the height vertical displacement. Here of let's say the tunnel advance, but of course this could also be done by tilt sensors, put in line in a daisy chained line here of mechanical mechanical beams that for each segment via its tilt, you can determine the incremental vertical displacement and accumulate this displacement in order to get from a initial reference point the displacement throughout the entire chain of measurements. Basically, this could look then like this: 3-meter beams with tilt nodes here. That's a rather old picture, but you saw it, for example, here previously. This is also a chain along the tunnel, measuring the vertical displacement along the tunnel. Yeah, and we were talking about the sensors, we were talking about nodes communicating with each other, communicating the data, the data outside. And all this data is then usually collected at a gateway. Above surface, we can power the gateway easily by a solar panel. But if we are in the tunnel, then we might have to collect the data at the gateway, power the gateway by the internal power supply. Usually in existing tunnels, at that point, we might have even cellular signal, and the cellular signal would be used then to communicate the data from the gateway outside through the internet to the cloud server where users have access. Or in case of tunnels where the telephone connection is not present, we might be able to communicate through the communication system of the tunnel, Wi-Fi or anything, the signal outside to a communication box where, for example, here it says still 3G, but today might be 5G systems via cellular signal. We can transport this data outside, and then it ends up on a cloud server where a certain platform, either our own platform or the user's individual platform, general platforms, the data can be visualized for trends and alarms. The system health can be monitored. The access to the system to change and modify, for example, recording rates can be accessed. Alarm messages can be sent. Access from everywhere, here, for example, via mobile phone to the platform can be provided. And then, of course, the data can be pushed forward into whatever software there might be. I just representatively showed here the big three in geodetic monitoring, where the data can be pushed to the platforms. Yeah, well, and in order to finalize this whole brief overview of, let's call it tunnel or tunnel related monitoring, I summarized a number of parameters that can be observed because the nodes itself, there are nodes that have implemented implemented sensors like tilt nodes or laser distance sensors, but also there are nodes, data communication nodes, where external sensors can be mounted to, like the strain gauges, pressures, anchor loads or so, temperatures, groundwater level, as we saw with piezometric or pore pressure, soil moisture, weather. There is a huge variety of geometric and geotechnical sensors that can be connected into via these nodes into a multi-sensor system. So exceeding basically what by wireless monitoring, exceeding basically what geodetic systems with total stations also can provide. Yeah, and then final overhead, just to say that, to mention that by these kind of connecting sensors, we have basically rugged equipment with low maintenance, easy autonomous systems by powering, for example, through solar panel, with long battery lives that basically provide also life cycle monitoring or so. We don't need line of sights for this. We have all the data in the cloud. Compared, for example, total station observations where individual measurements are sequentially one after another measured, all nodes can take the data basically at the same time, simultaneously. We have redundant data paths. We can connect or control and modify the system remotely, which is here my favorite sketch here. We have light wave equipment with no intrinsic value, with, of course, compared to expensive, for example, total stations, is not particularly attractive for any kind of thief stealing the equipment. And that, of course, all together with fast installation and easy handling means that it's far more safe, particularly if you're in unsafe environment like tunnels or rail track situations are. Yeah, and by this summary, I want to thank you for your attention and eagerly wait for your questions. I saw that I exceeded my time. I hope that this might be excused. And if, yeah, you are still interested in questions, feel free.
Okay, let's look at the questions that come through. Okay, so there's one that has asked, can you trigger a higher rate of readings when alarm limits are exceeded?
Well, I assume that this question means that if this can be done automatically. Basically yes, but it would require a certain impact. We do that with slope monitoring, where we have a low power accelerometer which wakes up during when a certain impact is noticed, and then it can be configured that the reporting rate is increased. We would have to figure out whether the impact is significant enough to trigger these kind of system. But of course, manually you can at any time increase on a system like this remotely the reporting rate.
Okay. Just another one. Is it possible to integrate the Sensieve tunnel monitoring data into other data viewing software so I can see all of my data together?
Definitely, yes. I mean, I tried to show that on the previous slide. We have at different levels, we have export options. We can access our database via API from the outside. So there can be a customized access to the database with reading out certain parameters and flags, or we can push our data via FTP to outside platforms. And in these platforms, of course, then all the data that we might not be able to visualize in our platform can be combined with data derived from Sensieve equipment.
Okay, perfect. There's another one that's come in. What if I need high frequency monitoring and want to use flat mesh but don't have a cellular connection in the tunnel? Is there a workaround?
Well, there are different options. I mean, we have customers that actually let the equipment record the data and then carry the gateway out to read out the gateway. But of course, that's no option if you want the immediate alarming. We would either try to communicate the data out to the outside, so combine the monitoring hub with a communication hub outside the tunnel. So we would have wired connection maybe between the gateway, or a Wi-Fi connection between the gateway and certain stages to the outside. It's a question that has to be solved individually. Of course, if we want data, if we want to get data out of the tunnel, then we need some kind of communication to the outside. Yeah. So we have mines in South Africa that use our systems. It might be, if longer distances are required, that alternative to the flat mesh system, we would use a LoRa-based system, where particularly in a tunnel can cover long distances. But yeah, we would have to solve that problem individually.
Okay. Someone else has asked, what about deformation monitoring ahead of the tunnel face?
This is an interesting question, because I just threw out this overhead, which I had for EPB machines, advanced, when you have earth pressure balanced machines that in advance in front of the machine. Well, basically, it's the same monitoring. It's basically at a certain time, we are talking about the vigilance zone. Yeah. So when we are at a certain station in tunneling, then we could calculate by the depth, by the overburden, and the ground conditions. We could calculate what kind of impact we could have on the surface in advance, and any kind of area that by the tunnel advance is already in this zone of impact would be considered already a zone of influence, but anything ahead would already be or would still be the vigilance zone. If you already know or I assume that you know the alignment of the tunnel, then of course you could install equipment ahead of the tunnel advance and monitor it all the time before the tunnel boring machine or the tunnel advance reaches that station, and then you have monitoring, in advance of for the advancing tunnel. I don't know whether this answers the question. For me, it's obvious that if I have a tunnel alignment, then I know on the surface where the tunnel alignment will be, and then I define the area of impact beforehand. Like if it's in a urban environment, then it would be a couple of buildings that are, for example, critical or infrastructure like bridges or railway tracks, and I would in advance equip these kind of structural buildings or so with equipment that when the machine advances or the tunnel advances and reaches this stage, then we have immediately the comparison between the normal conditions and the impacted conditions. I don't know whether this answers the question. I hope that it does.
I hope that it does, yeah. If it doesn't, then you can
send me a mail.
I'll send you an email, yeah. Okay, let's see what else has come through. Another question is, can the sensors store data if the network is out of order?
Well, the flat mesh sensors themselves don't store data on the node. Yeah, all the data is preliminary stored on the gateway, and we assume that the communication, a flat mesh system is a mesh network. So the nodes communicate among each other and transport via this kind of data paths the data to the gateway. And at the gateway, the data is stored in intermediately. So, for example, if the cellular signal is down, it would store the data, and when the connection is reestablished, then the data would be submitted. The data that has not been sent yet will then be submitted the moment the connection is reestablished. In case of the GeoOne, the LoRa system at Sensiv called GeoOne, the nodes can be configured in a way that they store the data if they don't, or if they store the data, and in case that no gateway, the data cannot be sent to any gateway for whatever reason, the data can be read out of, by the NFC devices, can be read out of the nodes, yes.
Okay, perfect. I think that's answered another question. I think you've answered that question. Someone just asked, can the data be stored locally on the data logger and then pushed afterwards in case there is a failure in communication or the server where the software is hosted goes down? So I think you've...
Yeah, well, as I said, we have different stages. We have the local network and the data. In case of a flat mesh system, the data of all the nodes reaching the gateway is intermediately stored there. There is enough storage space there to cover months of data if that would be required. But of course, the data is immediately sent to the server the moment the connection is reestablished.
Okay, perfect. I think I've answered all of the questions that have come through. Obviously, if anyone does have any more questions, you can reach out to Marcus, who's put his email address there. We've also got our info@sensive.com email address. So yeah, please feel free to send the questions there. Yes, okay. I guess we'll wrap up. So that brings us to the end of our 2025 webinar series that has flew by. I just want to take this opportunity to say thank you to everyone that has joined us so far. We will be announcing our January webinar in the new year, so please keep an eye out for that. Thank you so much, Marcus, and thank you everyone who joined us today. We just want to say happy holidays from all of us at Sensive. We're wishing you a joyful holiday season and a wonderful new year ahead. So thanks, guys.
Yes, same for me. Okay.